All right, hey everybody. My name is Xander. I'm a developer advocate at Arize AI. And today I'm going to be showing you a cool workshop on detecting drift for a sentiment classification model and finding the root cause of that drift using Phoenix. For those of you who haven't seen Phoenix before, Phoenix is our open source project from Arize, which is going to help you, first of all, get ML observability by detecting issues and finding the root cause. All right, so that's what we're up to today. Here's our agenda. We're going to start really high level and just talk about what is ML observability. I'm going to give you an overview of Phoenix, and then we're going to hop into the interactive portion of the workshop, where again, we're going to be dealing with an NLP sentiment classification model, and we'll reserve some time at the end for questions and answers. So let's just start really high level. What is ML observability? A machine learning system is said to be observable if you can, first of all, detect issues in production. That's called monitoring. And if you can not only detect those issues, but you can quickly identify the root cause of the issue. That's called root cause analysis. So in particular, I want you to remember ML observability is not just monitoring, it's more than that. We want to be able to detect issues like data quality issues, performance issues, and drift issues like we're going to see today. And we want to be able to quickly identify what is causing the issue so that we can get you to that actionable insight so that you can actually go and fix it. So that is ML observability in a nutshell. If you remember nothing else from this talk, just remember this equation: ML observability equals monitoring plus root cause analysis. And what is Phoenix? Phoenix is an application. It's open source. It runs in your notebook environment, and you can see that over here on the right. Literally, you can actually use Phoenix inside of your notebook if you want to, but it's an application that runs alongside your, on whatever server is running your notebook, whether that is your laptop, whether that is your Colab server, that's where Phoenix runs. And as I mentioned before, Phoenix is going to help you detect issues like data quality, drift, and performance issues. And we're going to see an example of a drift issue today. And if you actually look in the Phoenix UI, you can actually see how we're doing this. This graph up here at the top is actually measuring the drift of our production data relative to our training data over time. And you can see that right here in the middle, there's been some spike in the drift, indicating that there's been some kind of drift issue happening during this period of time. And we're going to dive into these details. And the third thing I want you to know about Phoenix is that Phoenix helps you pinpoint the root cause. So we're not only in the business of helping you detect the issue and raising an alarm bell, we also want to help you figure out really quickly what's actually causing the issue. That's root cause analysis. And in this Phoenix UI, you can see that in particular right here, where, as you're going to see, we're going to be taking your text data, representing it with what's called an embedding vector, visualizing those, and then automatically using Phoenix to surface up problematic clusters of data so that you as the user can quickly identify, oh, this is what's causing the drift issue, get to that actionable insight so that you can go and fix the problem. All right, so that is Phoenix at a very high level. Let me just pause for a moment. Yeah, and there will be time for Q&A. Any questions before we actually dive into the nitty-gritty? Okay. Looks like we're good. So I'm going to keep going. All right, so let's actually get into the details here. This is the NLP sentiment classification portion of the workshop. And I'm going to just set the stage here. I want you to imagine that you are in charge of maintaining a sentiment classification model in production. And this model is taking as input online reviews of US-based products, and it's classifying the sentiment of each review as positive, negative, or neutral. Okay, so imagine you work in an e-commerce company and you're in charge of the model that's actually making the predictions about, oh, is the review positive, negative, neutral? And you're noticing that the model initially performs well in production, but its performance is actually degrading over time. And you have been tasked with figuring out what is causing that performance degradation. So the goals for this workshop is going to be interactive, hands-on. I'm going to give you a Colab link in just a moment. Our goal is, first of all, to compute embeddings for your product reviews. And I'm going to show you how, I'm going to show you some of the tools that Arize provides that makes it really easy to do that. The second thing we're going to do is we're going to visually explore your embeddings and detect drift using Phoenix. And the third thing we're going to do is automatically identify that problematic cluster, again, to point out, hey, this is the actual data that you're seeing in production that is causing this drift issue that we've detected. Okay, so that is at a very high level what we're going to do. I'm going to go ahead and click on the link to the collab right here. Folks still able to see my screen? All right, awesome, thank you. Cool. So here we are in the collab, and there's a couple of ways that we can run this collab. So this particular collab, if you want to be able to run all, it's going to help to actually have a GPU. If you don't have access to a GPU on collab, don't worry, you'll still be able to run the notebook. I'm gonna first of all show you how to run it if you do have access to a GPU. So let's go ahead and connect. Looks like we are connected, and I'm going to go ahead and change my runtime type. That's down here. Change the runtime type, and I'm going to select a GPU hardware accelerator. Now, don't worry if you don't have access to a GPU or if you're out of credits, don't worry. We'll get to that in just a minute. Okay, so it looks like for me, looks like I've gotten that GPU right here. Next step is, if you have that GPU, go ahead and go up to runtime and press run all. If you don't have access to the GPU, you're going to need to actually run each cell individually, but you want to skip the cells that have this speech bubble emoji in front of them. In particular, you want to skip this cell right here. This is the cell where we're actually going to be computing embeddings, and that's going to benefit from a GPU. But I actually have the GPU, so let me go ahead and press run all. And I'm going to let that go for a minute, and it's going to start installing Phoenix, and we'll actually dig into the details of the notebook. So yeah, let's start digging into the details here. What are we doing in this notebook? We're first of all going to install Phoenix, pip install Arize-Phoenix. We're also going to install Arize auto embeddings. This is going to be the module from the Arize SDK that's going to help us actually compute embeddings for our product reviews. We're going to import those dependencies that we need. And we're going to start by downloading some data. And we're downloading two data sets. We're downloading a training and a production data set into two pandas data frames. And here I'm actually just visualizing what does my data look like. So let's actually go over what the data looks like here. You can see the first thing to notice is we've got this prediction timestamp column. That's just going to be the moment in time during which an inference was made. And in particular, it's not actually meaningful for the training data, but for the production data, we're logging the actual moment in time for which the inference was made. We've also got a couple of features here. I'm not going to go into these in too much detail. We've got reviewer age, reviewer gender, product category, etc. And here's the important part. We've actually got the product review right here inside of the text column. So what do these product reviews look like? Here's an example. Love these glasses. Thought they'd be everyday, some yada, yada, yada. Sounds like a pretty positive product review, and that is exactly what we're seeing here in the label column. So the label column contains the actual ground truth label for this example. We've also got the prediction from the model. We've got our prediction ID. This is just a unique identifier for each inference that was being made. And the last thing I want to call your attention to is the text vector column. This is actually the embedding data. So we've actually downloaded pre-computed embeddings for you. So if you don't have access to a GPU, you're going to be able to run the notebook still because, because these embeddings are right here in the data frame. But we're actually going to be recomputing this in the notebook if you do have a GPU, just so that you can see how you can easily get embeddings in order to get into Phoenix and see value. Okay, so hopefully that's clear in terms of the format of the data that we're dealing with. We're going to see more examples of these product reviews. So I think that will be very crystal clear in just a moment. And I'll mention that the format of the production data frame is actually roughly the same. I don't think there are actually any differences in this particular case. All right, and here's where we're actually getting into some of the fun stuff, which is we're actually going to be computing embeddings using a model called Distilbert, which has been fine-tuned on a data set of product reviews. That's what this code right here does. In just a few lines, I've actually computed all of the embeddings that were here in the text vector column. And let me actually dive back into my slides for a moment. And let's talk about how did we actually get embeddings. This is one of the challenging things, right? Is like, how do I get my embeddings? There's many ways of doing it, right? You could send your piece of text to the OpenAI embedding API. Maybe that's a really easy and low-lift way of starting. Another thing you can do is you can actually take the model that you're using in production, and you can extract embeddings from the model. And the advantage of doing that is that you're actually going to get insights into what the model thinks about your data. So that's what we're going to do today. We're going to use the Arize SDK auto embedding module in order to actually extract those embeddings. And in this case, the embeddings are being extracted from a Distilbert model, which again was fine-tuned on a sentiment classification task. And why is Distilbert a reasonable choice for a sentiment classification use case? It is an encoder-only model, which just means that it's going to take your input piece of text, it's going to condense it down and get a very nice single vector representation of your text. It's going to encode your text in a way that can be used to build a classifier on top of it. And we're going to get into that in just a minute. And I guess what is the history of this particular model? The Distilbert model is a smaller and faster version of BERT, which is a well-known encoder model using transformers. It stands for bidirectional encoder representations from transformers. And again, I think we'll show a slide in a minute that will just make this really clear. And the other thing I'll mention is that in this particular case, the dimension of the hidden states is 768. And so here's kind of like the flow, right? And this is like diving into the weeds a little bit. Don't worry if this doesn't totally make sense. It's not actually needed to run the notebook, but this is actually what's going on under the hood inside of the notebook. Is we're going to be taking a piece of input text. That input text is going to get tokenized. So it's going to get split up. So if the input text is a sentence like, I love Paris, it will be split up into a sequence of tokens. I love Paris. For BERT and Distilbert in particular, we're going to be adding on a couple of extra tokens. We're going to be adding on something called the classification token here at the beginning of the sentence. And we're going to be adding on a separation token at the end. We're going to take all of these tokens, pass it through the model, and what we wind up with on the other side are these output hidden states from the model. One embedding vector for each of the tokens that was input to the model. So in this case, you can see I've got a one-to-one correspondence between my input tokens and my embedding vectors. And I guess what is the important thing to note about these embedding vectors? BERT uses something called bidirectional attention, which just means that each of these tokens, each of these embedding vectors is actually considering information not only about this particular token, but also about the tokens that preceded it and the tokens that came after it. And this embedding up here in orange, the one that corresponds to the classification token, is actually a little bit special. This one, the classification token doesn't actually correspond to a word in the original sentence, but this one kind of captures the meaning of the entire input piece of text. In this case, I love Paris. And this is the one where, again, this is just an embedding vector of dimension 768. This is the one where you would build a sentiment classification head on top of the model in order to actually predict the sentiment into one of three categories. And importantly, when we're in the process of fine-tuning, when you're actually fine-tuning on the sentiment classification task, what happens is you are then fine-tuning not only this sentiment classification head, this task-specific head, you're also going to be fine-tuning the latter layers of the BERT model. So you're actually going to be tweaking the embeddings that you get out so that the embeddings that you're getting out, in particular, this embedding right here, is going to be like not only considering the input piece of text, but really looking at the input piece of text in the context of sentiment classification. So now this embedding, which is the output from the BERT model, after fine-tuning, it's really going to be talking about like, okay, what is like the sentiment of this input piece of text? So that was diving into the weeds a little bit. No worries if that was, yeah, sorry if that was too fast, but TLDR, this is the embedding that we're going to be using. It is the embedding from the BERT model itself, corresponding to this classification token. And all of that is actually just happening under the hood right here in this call to generator.generate embeddings, all happening under the hood for you. So now we've got this text vector column corresponding to each piece of text. Now we're actually going to use Phoenix. And as I mentioned, Phoenix is an application that you run in your notebook environment. In this case, it's an application that's running on your Colab server. And in order to use Phoenix, the first thing that we need to do is we need to actually tell Phoenix, what do the columns of my data frame mean? And that is what this schema field here is doing. It's just telling us, oh, we have a prediction ID column, we have a prediction timestamp column, we have a column called prediction label containing the prediction label, et cetera, et cetera. The important, maybe the trickiest part here is that we're actually also defining what we call an embedding feature. And that embedding feature is basically gluing together two different columns, the text column that contains the actual product review itself, and the text vector column, which contains the embedding data. Once we define the schema, we define a couple of Phoenix data sets, and then we actually launch the app. And if you click on this link, this is actually going to open the Phoenix UI. Let's give that a minute. I'm going to get a little bit of water. While that's loading up, any questions so far? Okay, looks like I'm seeing some discussions around BERT. Okay, yeah, so cool. Yeah, questions around BERT. We can chat about those at the end. Yeah, definitely think that's worth the chat. All right, so what are we looking at right now? Now we're getting into the fun part, right? Now we're actually using the Phoenix app. So again, this is an application. We're here looking at this homepage that's giving you an overview of all the different information that we've given to Phoenix. Here you're seeing the text embedding feature that we defined in the notebook just a moment ago. Here you're seeing some of those fields from the data frame that we went over. And really the place where all the action is going to happen for this particular example is here in the text embedding tab. So let's go ahead and click on that. And this is bringing us to that screenshot that I showed you at the beginning of the presentation. Let's let that load up. And again, what are we looking at here? Up here at the top is embedding drift over time. That's the drift of our production embeddings relative to our training embeddings over time. And you can see that we started out pretty good, low drift, low drift, low drift. And then at some point, the drift suddenly went up and there was this period of high drift and then it went back down. Okay, so that's what that graph at the top is talking about. And then down here in the bottom, what you're seeing is a low dimensional representation of your embeddings that you fed into Phoenix. So again, we computed these embeddings that have dimension 768. They're very high dimensional. And the first thing that Phoenix is going to do when it gets those embeddings, it's going to use a dimensionality reduction technique called UMAP in order to take those high dimensional embeddings, reduce the dimension down to 3 dimensions. That's what you're looking at on the screen. And let's actually come over here to the bottom left and take a look at our primary and reference data sets. In this case, our primary data set is our production data. So we have our production data in blue. We have our training data in purple. And the first thing I want to call your attention to, maybe let me stop this from spinning just for a minute. The first thing I want to call your attention to, let me just toggle this on and off. If you notice, the production embedding distribution and the training embedding distribution are basically the same. The purple and the blue points basically overlap. The two distributions look really similar. And that's the reason that up here in this graph over here, at this moment in time, we're not really seeing any drift in the graph because, again, the two distributions between training and production are basically the same. Now, let's go ahead and actually explore some of this data. This is the really fun part, right? This is the fun part, I think, where you get to actually explore the point cloud. And one of the really cool parts about this particular example is that because we are dealing with the embeddings that came directly from a model that was fine-tuned on sentiment classification, we're going to get this really nice gradient where you're going to see as we move from one side of the point cloud to the other, you're going to see the sentiment gradually change. So let's go ahead and dive into that. I selected the lasso right here. What that's going to do is it's going to allow me to select certain portions of the point cloud. So let me just select a few points right here at the rightmost extremity of the point cloud. Cool. All right, let's read a few examples here. Here's one product. Here's one product review. The example says, the rings are so cute and fit well. Here's another one. Granddaughters loved this product. Here's another one. The light on my soundbar is super bright. The large sticker from this set covers it beautifully, exclamation point. All right, so what are we seeing in this particular cluster? These are positive product reviews. And in fact, they're very positive, very enthusiastic product reviews, as you can see with all of the exclamation points. Now let's go ahead and move to the left. Let's select a portion of the point cloud right here. Okay. This one says, fits great button, snaps very positively. Okay. This one says, works great as long as you don't submerge, great product. Okay. So these ones look like, this one says, does everything it needed to. These ones are also positive, but maybe not quite as enthusiastic, right? Let's keep going. I'm going to circle this portion of the point cloud right here that's kind of at the left tip of this particular cluster. This one says, these are mighty tasty and having dry packs around as an option is handy, yet understand that 150 milliliters isn't very much liquid. This one says, I bought this to try instead of swerve due to cost. I haven't tried it yet, but I'm hoping it's great. This one says, swimsuits fit like a glove. Only thing that was annoying was that the cups they put inside to cover up. Oh, okay. Let's see, works as intended. I could use stronger peg for support. Okay. So basically the TLDR on this particular cluster is that these product reviews are kind of neutral. Some of them are like, oh yeah, it's pretty good, but it's not perfect, could be improved upon. So you're seeing as we move down, product reviews getting positive to neutral. Let's check out this portion of the point cloud over here. All right, made very cheap, but okay for the kids. The on-off switch is made in the plastic part that holds the Pikachu. Kids love it. Okay. The book is way better. Okay, so this is kind of like a little bit of a neutral to negative product review. A little too long, but so cute. Okay, so still kind of neutral. And let's go ahead and jump into the real negative ones right here. So I'm kind of in the middle of this cluster right here. It looks like new, but the package is so dirty and damaged. They were great the first wear, then they shrunk extremely and lost shape. Bent on the first slat that had 3 nails. So these are negative. And then of course, here are the really fun ones, which are the super negative reviews all the way out here at the extremity of the point cloud. Never received the product, 0 communication from the vendor, no way to run a business. This takes way longer than 2 weeks. They've taken my money and not given me the results. Don't buy, double exclamation point. So you're getting the feeling here, right? Like as you move from one side of this point cloud all the way to the other side of the point cloud, you're going from very positive to neutral to kind of negative to really negative product reviews. And there's actually a really cool way that we can actually visually see that in Phoenix. So if you come down to this color by drop down here in the bottom left, right now we are coloring the data by data set based on whether the data is from training or production. Let's go ahead and change this. So let's color by a dimension. A dimension you can think of as just a field of our data frame, right? And the dimension that we care about right now is the predicted label. And what you're seeing right here should just reflect the exploratory data analysis that we just did. In particular, you can see this point cloud over here on the right consists of all green positive product reviews, or this is the predicted label from the model. This point cloud right here consists of all the orange neutral reviews, and then here we get into the negative reviews. So this is actually, if you're building a model, this is like a nice gut check to say, oh, my embeddings are doing a good job at separating out the different classes that I care about into distinct parts of my embedding space. That should be a very reassuring sign to you. Okay. let me go ahead and switch back to data set. And now let's switch gears a little bit. We spent a lot of time diving into the point cloud because I think this is just such an amazing example of a really nice embedding distribution. But let's actually go back to the original goal. The original goal, if you remember, was we're putting ourselves in the mindset of the person who's in charge of maintaining this model in production. And we've noticed some kind of performance degradation. We want to investigate, right? And up here at the top, what you're noticing is drift over time, right? We've seen for some reason the model has drifted over time. And right now, we're only focused on this region over here on the right. We're only looking at production data from this window during which the drift was low. But let's say that we want to actually investigate what was going on at that moment in time in production when the drift was high. So to do that, I'm going to come over here and I'm going to click at this moment in time in the graph when the drift is high. And what's happening is that we're recomputing that point cloud, but now we're only going to be looking at production data from this window of time during which the drift was high. And if we actually rotate around our point cloud, you'll notice it looks a little bit different from before, right? We were seeing these two clusters before, and now all of a sudden we're seeing this this blue cluster of production data all the way out here in left field. We weren't seeing this before. All of a sudden, we're seeing this all the way out here in left field. It turns out that this is the actual cause of the drift issue. And you can tell because when I toggle on and off the blue data points, the production data points, there's no longer that perfect overlap that we were seeing just a moment ago. Now we can visually see that the actual embedding distributions have changed between training and production. And as you know, if you've trained these kinds of models before, a lot of the time, if a model is trained on a kind of data that is totally different, qualitatively different from the data in the training data set, if it's making inferences on a kind of data that's qualitatively different from the data in the training data set, the model's not likely to generalize well, right? So this is potentially problematic. And I could go through the exercise of just, using the lasso and selecting these data points manually. But the really cool thing that we allow you to do with Phoenix is we not only are going to reduce the dimension of your embeddings, we're also going to cluster those low dimensional embeddings. And that's what you're seeing over here in the left bar. These are the clusters of the low dimensional embeddings in the point cloud. And you can see, I think in this particular case, the algorithm is doing a very good job of selecting what I would probably choose as a human being to be the 3 clusters that I'm visually seeing in the data set. And we're not only clustering, but we're also going to be actually sorting these clusters, in this case, in ascending order of what we're calling cluster drift. And the cluster drift, you can think of it as just the proportion of, in this case, production data points relative to training data points in each cluster. So you can see at the bottom of each of these clusters over here, there's this blue and purple bar. And for this top cluster, the blue bar is almost all the way to the right, which just means that this particular cluster consists almost entirely of production data. And therefore, we're saying, Phoenix is automatically saying, hey, this is the problematic cluster that you need to take a look at, because this is where your data is basically all the way out in left field in production, and unlike anything that you saw during training. So let's go ahead and actually click on this example. And immediately, you can notice something very different about the examples in this particular cluster. In particular, all of these product reviews appear to be product reviews in Spanish. So what is the issue that we're actually catching here? The issue would be, oh, we have some sort of upstream data pipeline issue, perhaps, right? Maybe we've got an English and a Spanish version of our e-commerce site, and the traffic from the Spanish site is actually getting funneled to our model from the English site, right? And what is the actionable next step? Well, maybe it's, okay, we need to go fix our pipeline so that we're actually sending that traffic from the Spanish product reviews to a model that was fine-tuned on Spanish. Or maybe it's like, oh, we need to go grab a model that was actually pre-trained and fine-tuned on both English and Spanish product reviews, or a multilingual, we need to find a multilingual product review data set, right? And just in case you want to actually use these examples here, You can also actually export these examples back to your data frame. So that's what this button does right here. If you click export, what that's doing is it's saving these particular examples back to your actual notebook environment. And then if you come back here, let me see if I can remember the command. It should be session.exports. Yeah, and then -1. And here you go. These are the actual product reviews from that particular cluster. Now we've got them back into our data frame. So here you could actually go through some kind of active learning workflow if you wanted to, and go through the exercise of labeling these, and then fine-tune your models on your own product reviews if you so desired. So I think kind of ran through that pretty quick. Let me pause for a minute. It looks like we're about at time, but like I think maybe let's just have a conversation now. I'm going to take a look at the chat and just see. Looks like we have a lot of questions. Let me see. I'm going to just go in reverse order, and feel free to drop more questions in the chat. Have you thought of using a geometric shape for selection, like a sphere or a cube that could easily be resized? That's a pretty interesting question. I think I would pose the question back to you, like, would that make it easier though? I'm curious. Like that's an interesting thought though, like using a different selection shape for the actual selector. I'm not sure if we thought about that. At the moment, the way it works is we just you draw the lasso and then you project all of the points that are contained in the lasso from the camera's point of view. Can you go over how the drift is measured? Thanks, that's such a good question, right? So this question is around how are we actually measuring this drift at the top, right? All right, so how are we measuring it, right? Again, as I mentioned, the first thing you do is you select this point in time, and then we're going to be grabbing the production data from a 3-day window preceding this particular moment in time. We're grabbing all of that production data, grabbing all of those production embeddings. We're going to compute what is called the centroid, which is just taking all the embeddings and taking the average and getting an average embedding that is the centroid. We're going to do the same thing for the entire training data set. So take the whole training data set, compute a centroid. And what you're left with are these two embedding vectors, in this case of dimension 768, these two centroids. And all we're doing here in this graph is actually just computing the Euclidean distance between these two centroids, between our production data from this window of time and our training data as a whole. And it turns out that that very simple algorithm is actually pretty effective at measuring drift when you can represent your data with an embedding. What other distance measures do you currently support? Is Euclidean distance always the best? Okay, that's a pretty interesting question. So here's the beautiful thing, and we didn't really show you this in this particular notebook, but I would encourage you to go check out some of our other notebooks that do this. The beautiful thing about being in a notebook environment is that we actually allow you as the user to choose whatever metric you care about, to compute that metric in your notebook, and then to have that metric reflected inside of Phoenix, right? So it's tough to do that in this particular example because we don't actually have any metrics that are being computed in the notebook, but TLDR, like if you wanted to compute your own custom metric for each individual piece of text, you could do that, and then you would be able to actually visualize that metric. You'd be able to like color your data by that metric, and you'd be able to sort your clusters based on that metric to surface up potentially problematic clusters based on whatever evaluation metric you actually care about. I think there's probably a second piece to this question, which is the embedding drift algorithm is there another algorithm for detecting drift? And in this case, at the moment, this is the only embedding drift detection algorithm that we have built into the product. It's also the one that we found to work the best in practice. So this is our pretty strong recommendation about what you should use. But again, like I said, if you have the ability to define your own custom metrics, so you get to define the metrics you care about and then see it reflected inside of Phoenix. Question around the Pinecone notebook. We actually just had a workshop with Pinecone and LangChain. You can check out that video. Maybe Maggie, you could grab the link. Let me see. I'm getting hundreds of clusters when I select a data point in the area with high drift. That's interesting. So you may have gone to the, I'm not sure, maybe you went to the configuration setting over here and you changed some of these settings. These are the clustering settings. And if you change the configuration over here, you're gonna potentially get different clusters. So yeah, Joan, go ahead and see if you can just change it to these settings. Min cluster size of 10 plus minimum samples 1. Go ahead and change it to these settings and see if that works. And if it doesn't, go ahead and drop a message in community and I'll take a look at it. Yeah, thanks for stopping by, Andrew. Let's see, what else do we have? Yeah, cool. Thanks for the shout out, Julianne. Yeah, so a question, let's see. Primary use cases, production models, tracking where you are, training a new model. Okay, so this question is around what is the primary use case, right? And then there's another question around which dimensionality reduction algorithm we're using. So in this case, what is the, let's see, what is the use case here? What is the primary use case? So the story I told you today is around our approach for detecting drift, right? This is actually just one of many stories that I could tell you. Phoenix is a product that you can use for detecting issues like data quality, drift, performance issues. So if those other kinds of issues are of interest to you, I would go and check out our other notebooks. We're also getting into the space of LLMs and context retrieval systems. That's kind of like a totally different story though. But TLDR, the really high level objective for the project is we want to help you detect issues with your machine learning models and your applications, your machine learning applications, and we want to help you quickly identify the root cause of the issue. And a lot of the time, those issues are going to be issues in production, but it's not just production data. It's you could have put in you could have used this to check to see if your validation data set was drifted away, or if it was in some sense different from your training data set, for example, right? So it's not just production, but a lot of the use cases that we're dealing with are production use cases. The question around the dimensionality reduction algorithm. So there's a question around like, which dimensionality reduction algorithm are we using? In this particular case, we're using UMAP. We're doing that just because that's the algorithm that we have found to work best in practice for this particular use case. But yeah, let us know if you're interested in seeing other algorithms in the platform. If it's more about resizing, okay, so this is good product feedback. Thanks, Julianne. Like keyboard shortcut to quickly grow or shrink, tune the number of points you see. Okay, got it. Yeah, so these are product feedback issues. I think I'll make a note of these. Difficulty with the lasso. Yeah, so I think this goes back to the original point around like a cube or a sphere. So maybe like supporting different kinds of point selection strategies. And I think maybe some issues around usability. So thank you for the feedback, Julianne. I'll bring that back to the team. Let's see, can we use the learning from the cluster back in our model? So good question, Aditya. Maybe I think the question here, if I'm understanding correctly, is like, can I use this data in my model? And the answer would be like, yeah, totally. Imagine that you went through the process of deploying your model and you used Phoenix to actually identify those problematic production data points where you're seeing drift, where your production data is different from your training data, right? The idea here is we're going to help you identify those high value examples from your production data set that would be really high value for you to label and then fine tune your model on. So you could totally give that a go and treat that as the actionable next step, identifying the points that I need in order to fine tune my model. Is there a way to look at record by record with some drift score for each record? Swaroop, I'm not quite understanding this one. Maybe you can ping me in community and we can have a chat about it. I'm not quite understanding this one. Record by record, not quite understanding. What other distance measures do you currently support? Oh, I think I answered this one. Let's see. Drift. Sorry, just reading these. This one looks like a pretty use case specific one, Christopher. If you're still on, go ahead and ping me about this one and let's chat about it. Okay, so it looks like people were chatting about BERT and Distilbert. Does the embedding of SEP have any meaning? SEP is usually, it stands for separation. It's the token that you would put between sentences or at the end of the at the end of the piece of text there. How'd you come up with this, Dilbert? Oh, nice. Looks like this person is working on an agent. Dilbert, I don't know that was like it was just a model that we chose for this particular example. There's other models that you could choose too. I think the thing that would make a lot of sense for this particular example, though, because it is a sentiment classification use case, is to do some kind of encoder only model, of which BERT and Dilbert are notable examples. Yeah, we can send out the slides. Let's see. Thanks for the questions, everybody. Looks like that was just about it. Let me see. In a sentiment classification, each sentence text is a record. Okay. Yeah, let's chat afterwards, Sorup. If you can join us in community, I would love to chat with you. Oh, changing the min cluster size fixed the issue. Great. Okay, thanks. That's good to know, John. Thanks. What does the negative drift value mean? Okay, that's a good question. We come up here. Yeah, so the question is around this negative drift value. This cluster drift score, the question is like, why is this thing negative, right? I think that's a really good question. And this is actually like a piece of product feedback that we've heard before. It's kind of like something we're wondering about, like, what is the most intuitive or natural way for someone to understand this drift score, right? TLDR, the cluster drift score that you're seeing here is a number. It ranges between -1 and 1 in the current implementation. -1 meaning all purple data points, all training data points in this particular case. 1 meaning all blue data points, all production data points. And then a cluster drift score of 0 would be, you can kind of see it here, this is pretty close to 0. A cluster drift score of 0 would be perfect balance, a 50-50 ratio, a 1-to-1 ratio of production to training data points in the particular cluster. Hopefully that made sense. All right, cool. Thanks, everybody. Looks like that's all the questions that yeah, let me actually just jump back to the slides here for a minute. Slideshow, put out of this. Yeah, so just as a little bit of a wrap up here. Thank you so much for taking the time to come to the workshop. Hope it was useful. Please do let us know if it was useful. We're very active in our Slack community, the Phoenix support channel in particular. Drop a note in there if you run into any issues, if you have any usability feedback like the ones that were shared today. We really appreciate that feedback. We take it very seriously. We are a community-driven project, and without your support and without your feedback, we can't make the product better. So please do let us know if something's broken, or let us know if you'd like to see anything for your particular use case, any new features, anything like that. If you enjoyed the presentation, go ahead and check out our GitHub. Consider leaving us a star. It really does a huge amount to help us build the project and get the word out about Phoenix. And if you want to schedule a time to chat with me personally, you can Slack me. You can DM me in Slack, or you can also send me an email. My email is xsong@arize.com. And I think Maggie wanted to mention something about the Phoenix giveaway that we've got going on.
Yeah, we have a fun giveaway happening just to show our appreciation. It is linked in the resources section, and I'll also send it out with the recording and slides, a form to insert your address there so that we can ship you a small surprise. So look out for that as well.
All right. And all right, thank you so much, everybody. Really appreciate it. Again, let us know, join us in the Slack community. We love hearing from our users, and have a great day.